Okay guys, welcome to Lecture 9 of Introduction to Quantum Computation for the Summer 2020 offering at the University of Paderborn. So today's topic is in one of the central topics, of course, of any intro course to quantum computation, which is the quantum Fourier transform. And typically this also includes the application of quantum phase estimation, which of course will be included today as well. So the quote at the top of this lecture is by the very famous mathematician John von Neumann, which says, in mathematics, you don't understand things, you just get used to them. Okay, and there's a sense in which the Fourier transform falls under this quote, at least the way I interpret it, because certainly the very first times you see the Fourier transform, it just looks very mysterious, it can be a bit tricky to work with at first, but it's a very important transform, okay, and both classically and quantumly. Okay, so what I really want to stress, one of the, arguably, one of the most important lectures of the course will be this one, in the sense that even if you decide never to do quantum computation again, just like the entropy, the Fourier transform is one of these very central concepts that has applications far beyond quantum computation. Okay, and again, there are entire books written about this transform. So I have a bit of a blurb here in the introduction, so let me just kind of do my spiel and go through it, right? Which is that the classical, or I don't want to say classical versus quantum, at least not yet, but the Fourier transform, okay, it's very hard to understate the impact of this transform on our everyday lives. Okay, so for example, some of the examples in the notes, right? If you listen to a music file, let's say an Mp3, if you downloaded pictures off the internet, say your friends shared you pictures of their new kids or something, I don't know, right? Or you broke your leg, you needed an MRI, right? All of these things require the Fourier transform, every single one of them. Okay, so you have been using this thing on essentially a daily basis for the last 10-20 years at least, without even knowing it. Okay, so the question is, what exactly is the Fourier transform and why is it so useful? Okay, so very roughly, I'm going to approach this more from a signal processing perspective, because that's like the context in which I first learned about it. And so I first learned about the Fourier transform in a numerical computation course, I believe, at the University of Waterloo. And what we did there was, and this is kind of the perspective I'm taking here, is that the Fourier transform allows you to take a signal, for example, a sound file, okay, or it could be an image too, right? And decompose that sound file into its constituent frequencies. Okay, and so why is that important? Well, imagine for a second that you're talking about Mp3 compression, right? If I can take my sound file, like how am I going to take this big wave file, right, which is maybe like 50 megabytes, and squish it down into like 3 or 4 megabytes? Well, you have to throw something out, right? So what are you going to throw out without degrading the sound quality? Well, if only you could look at the sound file in a perspective that allows you to kind of look at the frequencies, which are ranging from very high to very low, and then you say, okay, these very high frequencies, the human ear can't really distinguish these very well, right? So there's no point keeping that data around. We might as well get rid of it, right? And same for the very low frequencies. And that's more or less what Mp3 compression does. And the way you do this, switching into viewing the file in terms of its frequencies, is via the Fourier transform. It decomposes the signal into its constituent frequencies for you. Okay. And so it's very useful in terms of signal decomposition, also for things like image processing, like for segmentation and so forth. But that alone is not enough to really make it ubiquitous in everyday life, right? The number two crucial thing is that the Fourier transform has a very fast near linear time implementation. Okay, so if you want to take an n-dimensional vector and apply the Fourier transform to it, then it only takes n log n time. Okay, so it's essentially linear time. And in practice, if something is not linear time or close to linear time, it's more or less useless. Okay, it's certainly for larger applications like processing sound files. Okay, so because of these two things together, this is why the Fourier transform is so ubiquitous in our everyday lives. And so I love to talk about the Fourier transform, and it's therefore not entirely surprising, or maybe I should say more that it's somewhat fitting, that the quantum Fourier transform is kind of at the heart of one of the field's most celebrated results, which is the quantum factoring algorithm. So now we should be very clear, right, that, the topic of Fourier transforms can be a bit messy, right? So if you just Google like Fourier transform or go look on Wikipedia or whatever, you're going to be, hit with a barrage of different definitions and so forth. So at least from the perspective of signal processing, there are 4 different notions of Fourier transforms, which I'll just very briefly mention, and I'll tell you which one we're thinking about, okay? So maybe I'll write this down. 4 types of Fourier transform, FT, right? This is my FT from now on. Okay, so and the way they go is as follows. So it depends on whether your signal basically is going to be continuous time or in discrete time steps, okay? And whether the signal itself is kind of infinite or whether it repeats, whether it's periodic or finite time. Okay, so the 4 types you might see are Fourier series, okay? And the names are, so the reason why I'm doing this is because the names can be quite confusing. They sound quite similar. Discrete Fourier transform, just Fourier transform, and finally we have the discrete time Fourier transform. Okay, so obviously these names are all confusing, and kind of what is the idea? How do you kind of distinguish between these two, or when does each of these get applied? Well, again, it depends on whether, so for example, for the very first one, the regular Fourier series, this is when your signal is continuous. Okay, so you have some continuous function f of x. Continuous, I guess that's the right spelling. And it's going to be, I think we want it to be finite. Okay. The discrete Fourier transform is going to be what happens when we have, well, obviously discrete, right? That's in the name. It's not continuous, the signal. So, f of x is going to come from some discrete domain. And it's also going to be finite. Just the Fourier transform is going to be continuous and an infinite signal. And finally, you have the discrete time Fourier transform, which, as you might guess now, is the last combination. A discrete signal, but which is not periodic. Okay, so, roughly speaking, these are 4 notions of Fourier transforms, which you might see if you look up, just Google it. And the one we care about in this course is this one, the discrete Fourier transform. Okay, so here, basically, we're going to have a discrete, the signal is discrete, so that means that our signal, quote unquote, is going to be given just by some state, or sorry, I should say state vector. Okay, you can think of it that way. So it lives in complex, and because it's finite, the signal is finite. I mean, we could cap this off at some finite dimension. Okay, and so we're going to be doing Fourier transforms of these signals, and so. Roughly speaking, the DFT is just going to be a linear map from Cn to Cn. Okay, so that means basically it's going to be an n by n complex matrix, generally speaking. Okay. And just as a heads up, you're going to hear a few things throughout this lecture, and it can be a bit confusing. So let me just kind of give you a very brief heads up of the terminology. Throughout, we're going to be talking about DFTN, which basically means the DFT transform that takes you from an n-dimensional vector to an n-dimensional vector. That is the mathematical transform, period. Okay, that's just abstractly what the math is. And then you can talk about implementations. Okay, implementations, and you have 2 choices, right? If you have the classical implementation over here, the fastest one is something called the fast Fourier transform. Fast Fourier transform. Okay, and very roughly speaking, the fast Fourier transform takes order n log n time. Okay, so it's near linear in the size of the vector. And then quantumly, we have what we're going to focus on is the quantum Fourier transform, which is, again, you should just think of it as an implementation of the standard DFT up to rescaling. Okay, and sorry, this is going to be the QFT n. This one I'll just call the FFTN. Okay, and the runtime for this thing is going to basically be order polylog n. Okay. So, on the face of it, it looks like, the Q of t is going to give you an exponential speedup. This is completely misleading. Okay, like technically these two are performing the same maps, but as we'll see later, the classical versus the quantum algorithm are, outputting completely different objects. Like one is going to be a classical description of the whole vector, and the other one is some quantum state. So they're completely different beasts. So you cannot really compare these. Okay, but just as a heads up, DFT is the map we're focusing on. And then you could talk about implementations of that map either classically via the FFT or quantumly via the QFT. So we're going to focus on the QFT. I'm not really going to show you the FFT itself, although that is very interesting in its own right, of course. But because the QFT, or the DFT generally speaking, is a linear map, it's an n by n matrix, rather than just kind of throwing this matrix at you right away, I want to give you a sense of where this matrix comes from and where do its properties kind of derive from in some sense. And I think the right place to start this story is by looking at the class of matrices from which the DFT arises. And that is going to be the set of so-called Vandermonde matrices. So Vandermonde matrices to the DFT. So that's section 1 in the notes. And Vandermonde matrices are a very cute construction. They go like this. Okay, so let's first do some recollections. Okay, let's think about lovely times in our lives where we say, given some complex number, let's just call it C, okay, we can define a geometric sequence, remember. So what is a geometric sequence? Well, it's going to be, C to the 0, which is of course just 1, C to the 1, C squared, C cubed, and so forth, right? You can always define this sequence. And, let me be precise. Maybe I'll let this go up to C to the n minus 1, because obviously n is going to play the role of dimension eventually. Okay, and so the nice thing about such sequences, of course, is that they have very strong structure, right? So, for example, if I were to take the sum of these terms in the geometric sequence, what we would call a geometric series. So if I write this out as k equals to 0 up to n minus 1, and I add this, right? In general, of course, you might not have a closed form for such a sum, but for a geometric series, you absolutely have a closed form. Okay? So this has a closed form. Okay? And, okay, so I'm not going to write it here, just Google it, right? So geometric sequences are very nice, right? They have a lot of structure, and so now we like working with matrices, right? So we're going to do something stupid, which is, what happens if I take these geometric sequences and I start embedding them into matrices? What kind of matrices do I get? And naively I might expect that they'll have some nice properties that I could work with. And so these matrices are called Vandermonde matrices. Okay, so, right now we have nothing to do with the Fourier transform, right? So here's, attempt 1, if you will. This is going to be not too bright of an attempt. So pick any complex number on which you want to define your geometric series. And now let's consider the Vandermonde matrix, M1 equal to, and what we'll do is we'll just embed, let's just say I'll just take it to order n equals to 3, so therefore the highest power is n minus 1, which is 2. And so for now, let me just embed the same thing 3 times. Okay, that's a valid matrix, I could define it. Okay, but of course this is not a very interesting definition because, I've just written the same row 3 times. So essentially this is a rank 1 matrix, right? These rows are all redundant. And it's just really embedding the original sequence. There's nothing new here, right? So that's not interesting at all. Okay. So, but something very interesting happens. Oops, attempt 2. If I now pick, and I really want to stress, distinct well, okay, let me not get there just yet. Let me just pick 3 numbers. And now we consider the analogous matrix, which I want to call M2. So here I have 1, C1, C1 squared, 1, C2, C2 squared, 1, C3, C3 squared. Okay. So this is, you know, potentially much more interesting. And indeed, what's really nice is that, fact, we won't prove this here. Okay. So M2 is full rank. Okay, so well, I should say maybe full row rank. In this case, of course, the matrix is square, so the number of rows and columns are the same, so full rank just means full either row or column rank. But of course, if you had, say, a different number of rows and columns, then you could talk about full row rank. Okay, okay, well, okay, let me be a little bit, because we're square, okay, M2 is full row rank, or full rank in general, if and only if all Ci are distinct. And so here I'm using the fact that M2 is square. If M2 is not square, then of course if you have more rows than columns, then obviously that, well, you have to be careful, I guess, how you define rank, okay? But it will saturate the dimension, basically, the smaller of the 2 dimensions, the row or the column rank. So let's just focus on square matrices. We'll say that it's a fact that M2 is full rank if and only if all these numbers you pick are distinct. Okay. So for example, I mean, an easy way to see that this is a necessary condition that the Ci are distinct are, you know, if I make C2 and C3 the same C, then I have 2 redundant rows. And so by you know, row operations, I could eliminate one of these rows, right? So when you take it to, say, row reduced echelon form or something like this, you'll see that this thing will be rank deficient. So you really need the C's to all be distinct, and it turns out that's also sufficient. Now, you know, ultimately what we're going to see is that if I just pick a very specific choice of the Ci, I'll get the DFT coming out. Okay, but before I do that, you know, Vandermonde matrices are just fun to play with in general. Okay, so it's worth taking a moment to just get a little bit more comfortable with them, because they do have a number of applications, and one of them is has to do with manipulating polynomials, basically. Okay, so here's an example of why are Vandermonde matrices useful. Okay. Oh, terrible. Okay. And so let's see. So here's one application, is multiplication by a Vandermonde matrix turns out to essentially simulate the idea of evaluating a given polynomial, P. Okay, let's imagine this is a polynomial from the complex numbers to the complex numbers. At, say, the points. And so I'm just going to continue working with our example M2, which I know is a 3 by 3 square matrix for M2. C1, C2, and C3. Okay, so if I take my matrix M2, okay, up here, and I multiply it by some column vector, that's going to be equivalent to basically evaluating a certain polynomial, basically at the point C1, C2, and C3. Okay, so let's very quickly see why this is true, and, you know, it'll also give you an idea of, you know, where this kind of geometric sequence comes into play, like why is that there? So let's do the following, right? This is the exercise in the notes. Consider polynomial p of x equals to 4x squared minus 3x plus 1, right? So what I can do is I can encode this polynomial as a vector, right? Just by encoding its coefficients, right? That tells me everything I need to know. So I'll call the vector psi, and I'll write it this way. I'll write the constant coefficient first, then the linear, and then the quadratic coefficient. And now, what do I do is, you know, if I take M2 now times psi, right, what will I get? Well, I'll get 1 C1, C1 squared, 1 C2, C2 squared, 1 C3, C3 squared, times 1 minus 3 minus 4. Okay? And now if you work this out, you'll see that what is the first entry? Well, the first entry is basically 1 minus 3c1 minus 4c1 squared, right? Whatever c1 is. I haven't chosen c1 explicitly, right? And now take a look at, what this is versus what this is, right? I mean, this is exactly, why do I have a minus sign in there? There should be no minus sign. This is a positive, right? So this is a plus, okay? This is exactly just this polynomial, right? Evaluated at the point c1. I mean, you're staring at it, right? And the other two will be the same, right? And so this is just because, when I plug in c1 into this polynomial, you're going to evaluate it at increasing powers, right? Constant, linear, quadratic. Well, here it is, constant, linear, quadratic, right? So intuitively, that's kind of what a Vandermonde matrix does for you in terms of multiplying out a vector, okay? So let's just return to the DFT for a second. I'll return to this theme of polynomial evaluation at the end of this Vandermonde matrices section, but I don't want to get too off track. Like I said, the Fourier transform is fun. It shows up in very strange places. But let's return to the DFT, right? Because that was kind of our goal. So a Vandermonde matrix is very simple, right? We just take, a set of numbers, Ci, complex numbers, and I just plug them. One goes in for each row of the matrix. I put in one of the numbers in its geometric progression, right? 1, C1, C1 squared, C1 cubed, and so forth. So what numbers should I choose, right? So it turns out that to get the DFT, what we need to choose is kind of the quintessential, if you will, set of n complex numbers. Okay, so what is the quintessential set of n complex numbers? Well, I mean, obviously this is a very hand-wavy statement. This is not a formal argument in any sense, right? And, well, okay, maybe let's think about it for a second, right? Let's see if we can sort of think about, if I wanted to define complex numbers in some sense, what feels kind of as the most natural, quote-unquote, basis to take in some sense, right? So remember that any complex number C is just r times e to the I theta, right? For some magnitude r and for some phase theta. Okay, so somehow, the magnitude is kind of irrelevant, right? It's just a rescaling. So let's just, chop that part off, right? So now we're left to, thinking about the unit circle. Right, so I have the unit circle. And now I get to pick my phases, right? And now the question is, what phase do I choose on the unit circle? And so intuitively, I mean, if I had to sample points off this unit circle, I only had n of them, right? What would I do, right? Would I kind of pick some sort of weird set of, skewed points that are all bunched together? Like, no, that seems very unnatural, let's say, right? Again, I'm totally making this up as I go, right? I mean, there's no formal justification for what I'm saying. This is more trying to give some intuition, right? The natural thing to do, kind of, if you want to kind of cover the circle evenly, is to choose points like this, right? To evenly distribute the points about the unit circle, right? Like this, okay? And these are the roots of unity. That's exactly how you get the roots of unity. Okay, so in particular, these guys here are the 8th roots of unity, because there are 8 of them, right? Intuitively speaking, okay? So what we're going to do is, I want to talk about the DFT n, so my vector is a dimension n. I'm going to talk about, the n, what I like to think of as the n quintessential complex numbers. Okay, and these are going to be the nth roots of unity. Okay, so what in the world is a root of unity? Well, where do they come from first, right? So what are roots of unity? They are roots of this fabulous equation, x to the n equals 1, right? So these are going to be all the numbers that if I raise them to the power n, I'm going to drop back down to 1. Okay, all complex numbers. So roots over the complex numbers. Okay, so over the reals, of course, there are only 2 roots, 1 and minus 1, but over the complex numbers in general, you'll get n roots. And why? Well, this polynomial is degree n, right? So the fundamental theorem of algebra tells us that we will have n roots over the complex numbers. Okay. Okay, so what are these things? Well, I mean, if you stare at the picture, it's pretty simple, right? I've got basically 2 pi radians in terms of my rotation space. I'm going to divide it evenly among 8 vectors. So obviously what I'm going to do is I'm going to take 2 pi and just divide it through by multiples of 8. And that will give me precisely the 8th roots of unity in this example. So the nth roots of unity, what are they? Well, I'm just going to write them this way. They're going to be e to the 2 pi I, right? And remember I said I'm going to multiply this by multiples of 1 over n, basically, right? So obviously first I'll start with 0 over n, and then I'll have e to the 2 pi I 1 over n, and then e to the 2 pi I 2 over n, and so forth. And the largest one I'm going to have is n minus 1 over n. Okay, why won't I have n over n? Well, if I have n over n, right, then I just have e to the 2 pi I. And e to the 2 pi I is just 1. And so is the very first number in the sequence, right? The sequence will start repeating itself. I've already wrapped myself around the circle. Okay, so that's why we stop at, a ratio strictly smaller than 1. Okay, so these are the nth roots of unity. And the easiest way to write this, rather than writing e all the time out, what we do is we focus on the first kind of non-trivial one, right? So this one's kind of trivial because it's just 1, right? Anything to the power of 0 is 1. This is the first non-trivial one, right? In this picture, it's this one here, right? It's e to the I 2 pi over 8. And of course, you could simplify the 2 over 8 part there. This is what we call the principal nth root of unity. Because once you have this one, you can generate all the other ones just by taking powers. Okay, so I'm going to call this thing, and not me, but it's standard to call this thing omega n. So rather than writing out this entire e mess. And once you do that, then you could rewrite this entire thing as, omega n to the 0, that's this one. Then omega n, then omega n squared, dot, 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 omega n to the n minus 1. Okay, and recall that omega n to the power n just wraps you right around the circle. You go back to 1. Okay? So these are the nth roots of unity, and this is what we're going to plug into our Vandermonde matrix. But before we do that, let me just do a sanity check, right? Let's just make sure we're following. Right, so let's think about what are the 4th roots of unity. Okay, so first, let's do the picture, right? In the picture, we're sitting on the unit circle, right? And so I'm going to subdivide that equally into 4 slices of pizza. Okay? And what are those 4 numbers if you're on the unit circle? Well, we know that, right? It's 1, minus 1, I, and minus I. So those should be the 4th roots of unity according to the geometric picture. And now let's just plug in this definition up here just to make sure we agree with this. So the principal 4th root is what? It's the one with the power 1. So it's e to the 2 pi I 1 over, and n is 4, so we're going to put a 4 here. Okay? So if I want, of course, I could simplify this and I could just write e to the pi I over 2. Right? Same thing. Okay, so now if we look at the 4th roots of unity in terms of this listing over here, right? Then what do we get? Well, we get, e to the, I guess I could just write it this way, e to the pi over 2, I to the 0, e to the I pi over 2 to the 1, e to the I pi over 2 to the 2, and finally e to the I pi over 2 to the 3. Okay, and so what are these? Well, of course, this is 1. Anything to the 0 is 1. This thing is just e to the I pi over 2, which is I, right? This one is e to the I pi, so you go 180 degrees around the unit circle, so that means you're at minus 1 now. And finally, this one is e to the I 3 pi over 2, so you've gone 3/4 of the way around the circle, and that, of course, is minus I. Okay? So this is why, I like to say that the nth roots of unity are the quintessential roots of unity, right? If you want to think of some representative set of complex numbers, this is a nice set to choose. Okay, so what are we going to do with these guys? Well, we're going to look at, these Vandermonde matrices, And you know, if I've got a 3 by 3 matrix, I'm going to plug in as these points. There will be precisely 3 roots of unity, 3 third roots of unity. I'm going to plug in those 3 third roots of unity into that matrix. Okay, so more generally, what is the definition for DFTN? Right, so this is going to be an n by n Vandermonde matrix defined by the nth roots of unity. And remember, you know, this is the set omega n to the 0, omega n to the 1, dot, 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 all the way up to omega n to the n minus 1, right? So we're just going to plug them in. So this is DFTN as a matrix. So let me just write the whole thing out first, and then we'll just sit and think about it a little bit. Okay, so, okay, maybe I'll just keep quiet and just write like I said. That's good. Sorry, let me just get this out of the way, save some screen space. Okay, good. And then dot, 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 and we get to omega n to the n minus 1, all to the n minus 1. Sorry, I want to make sure that it's clear that there's some space here in this matrix. So these are different columns. Okay, so this is the matrix. It's n by n, right? And what do we do? Well, we just do literally what we said. We take, you know, the roots of unity. This first root of unity is basically 1. And then I take 1 and I raise it to higher and higher powers, right? So 1 to the power 1, 1 to the power 2, etc., etc. And then I take the principal root, omega n to the 1, and you know, it goes in here. Okay. And then you put in this geometric sequence, right? Omega n squared, and so forth. And here you start with omega n squared, and then you square that up to the power n minus 1. So that is the discrete Fourier transform from Cn to Cn. Okay. Again, the first time you look at it, it's just a total S, right? And of course, by the way, you can simplify these expressions, right? I mean, so here I'm just giving you kind of like the brute force definition because I think it looks very natural once you come from the picture of Vandermonde matrices, right? But of course, if you were to just write down the DFT, you know, you'd simplify these. Like if you have numbers here that, you know, this is of course going to be bigger than omega to the n, right? Because it's going to, we're talking about the nth root of unity, but the exponent is, you know, 2 times n minus 1. So certainly this is going to wrap around the circle at least once. So then you could simplify this exponent, okay? Every time you wrap around the circle, you can ignore that revolution, right? Okay. Good. So now we have the discrete Fourier transform. So let's just do a little cute sanity check, which is what is DFT2? Okay. So now what is the DFT2? Well, you know, n now equals to 2, right? So we're looking at, you know, the second roots of unity. Okay, and again, we could draw the picture, right? What are these? Well, these are just going to be right here and right here, right? It's just 1 and minus 1. So these are going to be omega 2 is basically minus 1. That's right. And so then you're going to have, sorry, maybe I should be a little bit more formal, right? E to the 2 pi I over n, which is 2, right? And so this is minus 1. And so, you know, the roots, what are the roots? Well, they're going to be omega 2 to the 0, which is 1, and omega 2 to the 1, which is minus 1. So this sequence is 1 minus 1. So those are the two second roots of unity. So if I plug this thing into a matrix now, according to the definition of, this definition I have up here, what do I get? Well, the first row and column are super easy, right? It's just 1, 1. Okay, but then I, take the principal second root of unity and I raise it to power 1, so it's just -1. Okay, so stare at this for a second, and I hope you get a sense of deja vu when you look at this thing, right? Because you've been looking at this matrix since probably the second lecture, right? So what matrix is this? And if it helps jog your memory, normally you're used to seeing this matrix with a 1/2 in front, right? So this thing is really just up to scaling, nothing other than the Hadamard matrix. Okay, so indeed, if you want to do the 2x2 DFT up to scaling, it's just a Hadamard. So you've been doing Fourier transforms this whole time, you just didn't call it that. Okay. So so that is the DFT, and maybe I'll let you work out, in this exercise you could also work out DFT3, so maybe I'll let you work that out on your own just so you feel comfortable. Now, so this is a Vandermonde matrix, right? Now, what did we learn about Vandermonde matrices? Well, we learned that if I plugged in distinct numbers, Ci, right, the matrix I got was full rank, right? And if the matrix is full rank and it's square, then it's going to be invertible, right? So let's look at DFTN, right? DFTN, we plugged in the nth roots of unity for an n by n matrix, Vandermonde matrix, and so therefore, it's going to be full rank. And now the question is, what is the inverse of this thing, right? And I've sort of already given away the answer, right? I had this saying for, I guess, for Deutsch's algorithm, right? For the lecture where, where there's smoke, there's fire, right? And this is a good example of that, again, with the positive connotation, where, when we looked at the DFT2, it was not just invertible, but it was a very special invertible matrix, right? It was a unitary matrix. And indeed, in general, it turns out that DFTN is a unitary. So the inverse is very easy. It's just take the dagger of this matrix. Okay. So so since the nth roots are distinct, the DFT and matrix is going to be a full rank, and it will be invertible since it's square. Okay, and full rank. Okay. So, but actually, DFTN is unitary. Okay, so it's much stronger than that. Okay, so the inverse is very simple. This means that therefore its inverse is you just look at the matrix and you take the dagger of that matrix. Like, that's it. Okay, so now I'm cheating a little bit, okay? It's not quite unitary because, look at this thing here, right? Was this the Hadamard? Not exactly, right? It was the Hadamard up to this missing scaling factor. The scaling factor here was 1 over square root 2, right? That makes it unitary. So the DFT itself is not unitary, but if you rescale it, but of course, okay, if you do DFT times DFT dagger, you'll get something proportional to the identity. You'll get n times the identity, in fact. Okay, so let me be clear, this is a lie. Haha, right? More accurately, if I do DFTN, and I'll let you work this out on your own. These are the exercises that show that, you want to prove that the rows of the DFT are orthogonal, right? So once you do that, you could work this out very easily. You'll find that you'll get n times the identity. Okay, so it'll be diagonal, but it'll just have n everywhere on the diagonal. So if I want to make this thing unitary, the only thing I have to do is just modify the definition so it's renormalized. That's all. Okay, so this is unitary. Okay, so now I'm being honest, right? That is a unitary matrix now. Good. So typically in this lecture henceforth, when we talk about, the DFT, we're talking about this renormalized DFT so that it becomes unitary. So why in the world do we care if something is unitary? Well, obviously, this is a quantum course, right? Unitary operations, we can have a hope of applying on a quantum computer, okay? So this thing implies that we can apply 1 over root n, this normalized thing as a unitary circuit, okay, on a quantum computer. The only question, of course, is, how many gates do I need to do this, right? So the main question is how many 1 and 2 qubit gates to implement this, right? And there's a bit of a problem, right? Because typically the number of qubits for us, which is kind of the metric with respect to which we measure efficiency, the number of qubits is exponentially smaller than the dimension for quantum states, right? There's this blow up, right? So here there's a problem, right? For dimension, okay, let me do it the other way around. So if you have an n qubit state, psi, right? Where does it live? Well, it lives in C2 to the power n, right? The space is huge. Oh, sorry. It's C2 to the power little n, right? And so I'll call this C to the n, basically. Okay, so in other words, the dimension we're talking about is exponential in the number of qubits, which is the complexity parameter. So what we want, is an implementation that uses only polylog n gates, right? Because otherwise, as far as the quantum computer is concerned, it's not going to be efficient, right, in the number of qubits to represent that dimension. Okay, but nevertheless, it turns out we can do this efficiently. Okay, polylog n time. Okay, and let me be clear that in this lecture, whenever I say the words, Q of t n, essentially what I'm referring to is the DFT, this normalized DFT, of course, but very specifically, we're going to refer to the quantum implementation of that transform. Okay, so it's the same map, right? But we're talking about, how do we implement this thing on a quantum circuit? That's why it's called a QFT now. Okay, so it's the circuit, well, I should say the quantum circuit implementation of the, the normalized DFT. Okay, so don't be fooled. It's really the same map. Okay, so just like the FFT is the classical implementation of the DFT, the QFT is the quantum implementation. Okay. And again, let me be very clear that this looks like, we're going to get an exponential speed up because this thing is polylog n gates, much smaller than the dimension. But again, the output of this thing is going to be an actual quantum state. Okay, but let's revisit this again later, maybe. Let's just very briefly go back and have some fun. I mean, not that the QFT is not fun. Of course it's fun, but finally back to polynomial evaluation. Okay, so let's just forget about the words quantum again for a second and just have some fun playing with the Fourier transform some more. Okay, and basically the point is that you can use the DFT and more accurately the fast classical implementation of it. Okay, so same map, just a fast classical way of doing it, right? To multiply two, I think it's degree n minus 1, yes, good. So 2 degree n minus 1 polynomials, P and Q, in order n log n field operations over the complex numbers. Okay? So normally if I wanted to multiply out, 1 plus p, sorry, I shouldn't say p. So normally if I wanted to multiply out p times q, right, at some point x, right? The way I would do this is, I would expand out p, which is maybe 1 plus 2 x plus x squared, right? And then I would expand out q, which might be something like 1 minus 5x minus x cubed squared, whatever, it doesn't matter, right? And when I expand this out, the number of cross terms is going to be quadratic, right? The normal runtime for this multiplication would be whatever the degree is, right? In this case, the degree is 2 squared. And here, you get a really nice improvement. You can do it in n log n time. Okay, so how do you do it? And I'm not going to spend a lot of time on this because this is a quantum lecture, but this is in the exercise in the notes. The way you do it is basically what we sketched earlier, which is that you use the fact that multiplying by the DFT matrix, or by any Vandermonde matrix, allows you to evaluate a polynomial at the point ci in that matrix. So in particular, what you do is you use the FFT to quickly evaluate p, the polynomial p, at the nth roots of unity. Okay, and quickly means in order n log n time. Okay. And you also do this for q, of course. So by using the FFT, basically I just multiply by the DFT, and it will have that effect of evaluating each of these polynomials, remember, at the points in that Vandermonde matrix, which are the roots of unity for the DFT. Then step 2 is you can use pointwise multiplication okay, because what I can do is, after step 1, what do I have? Well, I've got p of 1, p of omega n, p of omega n squared, and so forth, p of omega n to the n minus 1, right? So that's what I get out of step 1. When I multiply by the DFT matrix, it evaluates it at the roots of unity for me, and it gives me this vector, right? And, this symbol here is going to be something that's sometimes called the Hadamard product. It's just entry-wise multiplication. You forget about the fancy name. And then, we know from step 1, the other thing we get is, q evaluated at all the roots of unity. Right? And so if I want to know what is p times q at these points, at these roots of unity, well, you could just pointwise multiply, right? Meaning, p of 1 times q of 1, right? This is just going to equal to, pq evaluated at 1. It's the same thing, right? You can just do it pointwise. It's much faster. So p of omega n to the n minus 1 times q of omega n to the n minus 1, right? This is just equal to the same thing as if I had first multiplied the polynomials out and then plugged in this value. Okay, so this takes only order n time because I've got 2 n-dimensional vectors and I'm just multiplying pointwise. Okay. So now I have, the polynomial pq evaluated at n points. I know its values at n points. And now I just want to recover the polynomial. And intuitively speaking, remember that, whenever I have a degree n minus 1 polynomial I've evaluated at n points, I could always interpolate back and recover a unique polynomial that fits through those n data points. Okay? And the way you interpolate, so interpolate the set of data points, these guys, to recover the unique polynomial p times q, and then of course takes in a parameter x. Okay. And the interpolation essentially boils down to doing an inverse Fourier transform, it turns out. So you just run the inverse FFT. Okay. So I don't want to say 2 more. This was supposed to be a high-level sketch. Of course, this will be also n log n because via inverse FFT. Okay. And one of the exercises in the notes gets you to prove this interpolation theorem, right? That Well, okay, you don't necessarily have to do it. You don't need the FFT to do this, right? You just need to think about Vandermonde matrices. And you can prove using Vandermonde matrices and just basic linear algebra that if I have a degree n-1 polynomial and I have evaluated at n distinct data points, then I can always recover a unique polynomial which fits those n data points. Okay? Again, the beauty of Vandermonde matrices. Okay, so that's it. So the reason why this is going to be faster, by the way, than the naive algorithm is because instead of explicitly multiplying these guys out, we basically went into the Fourier domain and did a pointwise multiplication, which was much cheaper. It's just order n. And then to convert in and out of that Fourier domain is n log n. Okay? Of course, this has absolutely nothing to do with quantum. I'm just saying this because it's fun. Again, it's important to understand the many applications of the Fourier transform. I cannot understate its importance. So, and by the way, just to help you kind of think about this thing, when you apply the Fourier transform in terms of signal processing, what it's doing, remember, it gives you that, it allows you to decompose a signal in terms of its constituent frequencies. So that's why, we tend to say that, the original signal is in the time domain, right? But once you apply the Fourier transform, it has the effect of rotating you into a different basis, which represents the frequency domain. Okay, so then the x-axis should correspond to your different frequencies. Okay, and then the y-axis presumably should be your weight on each frequency essentially. Okay, good. All right, so let's return to the quantum world. Okay, so I hope this gives you a good idea of what is the Fourier transform, where does it come from, right? So it's just basically a special case of a Vandermonde matrix where we plug in the nth roots of unity. Okay, and lo and behold, this thing is unitary, so we can hope to implement it quantumly, and that's exactly what we're going to do now. So again, when I say quantum Fourier transform, I'm realistically talking not about a different transform. It's the same thing as the DFT normalized. It's just the quantum circuit implementation of it. Okay, so again, to be clear, suppose we have an n-qubit system. Okay. And now we implement, and here let me write this in red to really make this stand out. So q of tn, how am I defining it? 1 over root n dftn, right? Because that was unitary via 1 and 2 qubit gates. Okay, so that's the name of the game. So how are we going to do this? I think the nicest way to do this is just to start with a small baby case, right? And then once you see the analysis for this, I think it's fairly straightforward to generalize to arbitrary n. So let's start with the n equals to 4 case. Okay, so here the Fourier transform is just a 4x4 matrix. Okay. So remember that if I want to specify a linear map, right, fully tell you what the action of it is, it suffices for me to tell you what is its action on any fixed basis. Pick your favorite basis. So let's pick the standard basis, right? And why do I like the standard basis? Well, remember that if I do, the q of t 4, remember we're talking about the n equals 4 case, and I apply it to one of the 4 standard basis states for C4, what is it going to do? Well, it's just going to extract the jth column of the matrix q of t4, right? This was one of the tricks. If you multiply by the jth standard basis vector, it extracts the jth column. Okay. So all we have to do is just understand the action of q of t4 in each of these 4 standard basis states, and that'll tell us what the full matrix looks like, right? And it'll turn out that by analyzing this column vector description, we're going to be able to decompose this thing into a nice circuit. So first, let's just write down the explicit definition just based on the matrix, right? The matrix told me that I should do 1 over square root of 4, right? Whatever n was, times the sum of k equals to 0 up to n, which n minus 1, which is 3. And then I'm going to sum over all the possible rows, right? And in each row, what do I do? Well, I plug in this phase, e to the 2 pi I. Okay, so there are two important terms here. One of them is j, right? So here's j, that's where this j comes from. Okay, so here I'm literally just ripping out the jth column of the matrix here. Okay, and the other thing I want to point out is k. Right, I'm going to write this in green. And remember, we're talking about nth roots of unity, so everything had this over n normalization, right? Okay, so, if you want to be explicit, this is a half times what? Well, it's going to be, basically 0, right? Because when k is 0, the exponent goes to 0. Plus, when we plug in 1, we'll get e to the 2 pi I j over n, right? 1 plus e to the 2 pi I j, I guess I should say 2 over n, right? 2 plus e to the 2 pi I j 3 over n. Sorry, I shouldn't say n, of course, because I know what n is. Over 4. Okay. Okay, this is also over 4. And this is also over 4. Okay. So, we could further simplify, of course. 0 plus e to the I pi j over 2, if you like. 1 plus, okay, and so forth. The simplification is maybe not so important. Okay, so, that's just the definition, and, we're going to focus on this kind of abstract formula rather than writing it out because, this will allow us to generalize later to arbitrary n very easily. Sorry, so here, same mistake here. I should not write n, of course. I should write 4 because I know, ooh, let's not do that. Because I know exactly what n is. Okay. And I want to keep the 2 here in general just to remind you that, 2 pi is, of course, a full revolution around the unit circle. And, this thing here, k goes from 0 to 3. So you'll notice how, k over 4 is always a fraction between 0 and 1. So you're never going to make more than a full revolution around the circle, right? And if you did, it would be redundant. So there's no point in doing that. Okay, so now why did I, another reason, why did I write k over 4 here, right? I could have put the 4 as the denominator over, j over 4 instead and left the k alone. So there's going to be a good reason for that. And let me just remind you of something, sorry. So think back to your programming classes, right? I know in quantum computing we don't do much programming, but, think back to programming. If you have, you're worried about implementation times or actual run times in practice, right? And you want to divide, your favorite integer by some other integer. In general, division is expensive, right? It's not a fun operation to do, right? It's much slower than, say, addition or something like this. But there's one type of division which is blazing fast. It's super quick, right? And that is when you want to divide by a power of 2, okay? So if I divide an integer k, right, by 2 to whatever, right? Actually, let me be consistent with my notes here, right? So here I said if I want to divide some integer a by, say, 2 to the k. So i.e. I want, a over 2 to the k. So how can you compute this super quickly, right, without actually doing division, right? The computer doesn't even need to do a division. Is you just shift the bits over. Shift the bits of a, I guess you want to go, okay, the decimal point goes to the left, right? So shift the bits of a to the right by k positions. Okay, so whenever you're coding, you want to do a division, it's by a power of 2. You never do a straight division, right? You look up in your programming language how you do the bit shift, and that's much faster, right? Okay, good. So let's do a quick example of this. Suppose that the number a is equal to 3 in decimal. So the subscript 10 means that I'm talking decimal. And so in binary, of course, this is just 1, 1. Subscript 2, that's binary. And so if I think about a over 2, right, what is it going to do? Well, it's going to, in decimal, of course, this is what? This is 1.5, right? But how about in binary? Well, you don't have to do any division. You just take this thing. And of course, we imagine here that there's a decimal point. Okay, and then when you look at the decimal point, remember, this is for inverse powers of 2, right? 1 over 2, 1 over 4, and so forth. And all we do is we just shift this thing over to the right one. So it's 1.1, and then a bunch of zeros, of course. Okay, and this is in base 2. Okay, and why is this true? Well, what does this mean? Well, of course, this is just 2 to the power 0, which is just 1, right? And this is 2 to the minus 1, which is a half, right? So that's why, this binary number represents 3 over 2, exactly what you want. Okay, so why am I saying this? Well, over here, there's a reason why I wrote this is because I'm going to do exactly that, right? So k is going to be some, in this case, we're talking about numbers from 0 to 3, so k can be represented with 2 bits, right? So when I do k over 4, it has the effect of basically just shifting everything to the right of the decimal place. Okay. So let's see what this buys us, right? So let's rewrite k in binary as, ket k, right? So these are the bits. These are the bits now of k. Okay. So each of these is, of course, 0, 1. What do we find? The q of t for applied to j, right? I'm just going to take the exact same expression as before. So let me just copy that. Where's that expression? Right there. Okay, good. Just barely fits. 1 over 2, right? The sum over k equals to 0 up to 3 of e to the 2 pi I j. Let me just copy it first. K over 4 times k. Okay. And so now let me just do exactly what I said, right? The bit representation of k is k1, k2, and then 0.0 technically, but now I'm going to divide by 4, right? So that's going to move the bits, I could have, okay, let me maybe be a little bit more precise. I can think of this thing as, I'm writing zeros just to give you, just to be clear that, there's a decimal point here to the right of which there are zeros here. So I could always rewrite k that way in binary, right? But now I'm dividing by 4, so everything's going to shift to the right. So I'm going to shift everything to the right by 2 positions. And so what do I get? I get 0.k1, k2, and then, of course, zeros. Okay, maybe let erase that so I don't confuse you. This and k. Okay, so I can always rewrite things that way. Okay, so but why am I doing this? Well, once we do this, then we can kind of break things down into a product structure, it turns out. So even though k technically acts on 2 bits, I can actually, if the input is just some standard base state j, I can always write the output as a product state as well. Okay. So in binary, let me expand this now in terms of, powers of 2, right? So this is a half, k equals to 0 up to 3, e to the 2 pi I j, and then, k1 times 1 over 2 plus, let me be consistent with my notes. Okay, maybe I shouldn't write it that way. Maybe I should write it that way. Okay, k1 times a half plus k2 times 1 over the next power of 2, right? A quarter. Okay, and this is just k1, k2. Okay, so now why in the world did I do this? Like I took this finding binary number and I opted to rewrite it in terms of its expansion, right, in terms of powers of 2. But the reason why is because, well, this is an exponent, right, of a scalar. It's e to this thing. And we know that whenever I have e to something that's a sum, I could split that into a product now, right? So let's do exactly that. So I could really rewrite this as e, first let me just write the scalars out, or the phases out. k1 times a half, and e to the 2 pi I j, k2 times 1 over 2 squared, or a quarter. Okay, so that's just breaking that apart into pieces. And there's no point keeping these two together now, right? Because, you know, this guy only depends on K1. This one only depends on K2. So I might as well also, you know, factorize now the actual states themselves, right? So I could actually write, let me put just a big half in front. So the constant stays the same. But what I could certainly do, oh, let's type on the notes, gotta fix that. K1 equals to 0 up to 1. So I could just cycle over the values of the first bit. Here it is. That's K1, right? Because this is just cycling through all 4 possible values. And here I can do the same thing, right? I could cycle through all the values of the second bit. Okay, now of course here implicitly there's a tensor product, you know, just to be very clear. I could always rewrite the state this way. Let me make just a quick note so that I correct this typo later on. Okay, good. So now that I've kind of factorized things out, now that life is really good actually, because my sums only have 2 terms. K equals 0, so ket 0. K equals to 1, ket 1. So let's just rewrite it in terms of ket 0 and ket 1. So I've got ket 0 and I've got ket 1. And likewise here I've got something with ket 0 and something with ket 1. Okay? And so what are the corresponding phases, right? Well, when K1 is 0, you know, then this is 0, and so the whole thing is going to go to, the exponent goes to 0, so the scalar in front is actually 1. So the more interesting case is what happens when K1 is 1, right? And then you're just going to get, you know, this thing as is basically, right? So you're going to e to the 2 pi I j over 2, okay? And likewise on the right side, you know, 0 picks up a phase of 1, and the 1 picks up this relative phase of e to the 2 pi I j over 2 squared, okay, or over 4. Okay. And now j, I could rewrite, just like before, I could write it in its binary expansion as well. It's going to be a number, you know, it's one of the standard base states for C4, so it's labeled by, you know, 0, 1, 2, or 3. I only need 2 bits to represent it. So I could write j this way, j1, j2, right? And so, you know, I could kind of reverse this bit shifting trick, right? I could write j, when I divide it by 2, I'm going to shift the bits of j over to the right one. So let's do this. 0 plus e to the 2 pi I, and then I'll get technically j1 point j2, right, in binary. So, you know, this is in binary. And then here I'm going to get 0 plus e to the 2 pi I, 0 point, and now I shift by 2 elements. Okay, there it is, 1. Okay, that's what I get. Now I'm going to play a little bit of a magic trick, which is not that magic, but maybe the first time you see it is kind of magic, which is I'm going to make this thing go poof. Okay, this j1 in here. So I claim that this is actually equal to 0 plus e to the 2 pi I, and, you know, let me just write this in red to really clarify that something is happening here. Let me not write that one in red. There. Okay, I'm just going to change that. Everything else will stay the same. So I claim that I can drop this, the j1 exponent over here. Okay. So why is that true? Right, okay, this is actually a good exercise. I'm actually going to leave this as an exercise. So it's an exercise in the notes. So I'm going to ask you as an exercise, you know, why? Why can I do this? Okay, oops, I'm missing a ket 1. Okay, so think about what it means to have basically a whole number on the left of this thing. Okay. Good. So what this says is that, you know, if I want to, good, so let's kind of take stock for a second. What have we done? I took the, you know, I wanted to understand, you know, what is the action of the QFT for on an arbitrary standard basis state for C4, okay? And because hopefully by staring at it long enough, you know, we'll try and figure out a circuit implementation of this, okay? And so what we did is we wrote this out And we came up with this, so this is the brute force formula for it, but then we realized we can factor it in this way, okay? And now the question is, okay, well, things are looking kind of good, right? Because, I've got a tensor product here, right? So, if I had, two wires coming into my circuit that's trying to implement this QFT, if I could do something here now and something here now, you sort of feel like maybe you can get, maybe this first one would be able to prepare, this guy over here, and this one would be able to prepare this guy, and then you'd get the output over here of, the QFT4 coming out, right? So it's not exactly that simple, but, that intuition is roughly correct, okay? So the first question we'll ask is, or maybe I shouldn't do a question, but let's do an observation. Okay, so let's look at, in general, what does, how can I sort of insert this kind of funny 0.j thing in? Like, let's suppose I just wanted to do this thing, right? So how to prepare 0 plus e to the 2 pi I, and then, call this whatever you want. I mean, I'm going to call it, take your favorite bit b. It really doesn't matter what it's called. It's just some bit b, okay? So b is just some bit. Okay, so up here we called it j2, but, I'd want to give you an abstract statement, right? If you want to prepare the state, well, how do you do it? So just think about what you're looking at, right? If b is 0, then the state you have is what? It's 0 plus 1, right? I mean, up to normalization, right? That's the state it is, right? Okay, that is the state it is. I mean, and then we have to renormalize to make it quantum, right? But that's all it is. The phase disappears, and if b is 1, right, then what happens is you get 0 plus e to the 2 pi I, 0.1 in binary, right? What is 0.1 in binary? Well, that's nothing other, than e to the 2 pi I over 2, right? 0.1 in binary is just a half. Okay, and what is this thing? That's just e to the pi I, right? It's just halfway around the unit circle. So this is just -1. Okay, so what have we learned, right? If I want to prepare this state here up to normalization, what am I doing? Well, I'm just preparing a plus state, or I'm preparing a minus state. Okay, and we know which gate does this, right? It's the Hadamard. The Hadamard gate does this for us. So therefore, if I do, the Hadamard gate applied to b, the bit b, it will do exactly what I want. 0 plus e to the 2 pi I 0.b. Okay? Okay, so this is a magic trick. If I could draw better, I'd draw some sort of rabbit coming out of a hat, but that's not happening. Okay, and if you're worried about this normalization, don't worry. I mean, that's just this thing over here, right? I mean, there are two copies of 1 over root 2, one from each of these brackets, and so you'll get a half in front. Okay, so this is wonderful, right? This is really wonderful because we're making progress. I know how to prepare this state. It's just a plus state right now. Now, how do I do this one, right? So I know how to inject J1 in, but now I want to kind of inject a J2 again into the second slot. Okay. So what do we know? Well, right now we know that Hadamards seem to do something for us. Right, again, so let me maybe put a box around this because this is kind of our target. This is what we want to prepare. So here's a naive attempt. What happens if I just do, therefore, remember, I'm trying to simulate the QFT on this input state J, and I'm trying to make it look like this thing, right? With a circuit consisting of 1 and 2 qubit gate. So I just learned that when I do Hadamard, it does something nice for me, right? So what happens if I just blindly do the Hadamard, on qubits 1 and 2, on J1 and J2? Well, then you're going to get a half times 0 plus e to the 2 pi I, 0.J1, right? Tensor, 0, sorry, plus e to the 2 pi I, 0.J2, 1. Running out of space here. Of course, I do have an infinite canvas. Kind of makes life easy. Okay. So is this what we want? Not exactly, right? So let's take a look at this for a second, right? What I wanted was I wanted J2 in the front, and then I wanted J1, J2, right, in my phases. And here, you know, I have something sort of like that, right? Maybe let me just get rid of this binary here to just reduce the amount of notation in this picture. Okay, now I don't quite have that, right? I do have a J2, but it's not in the first position, it's in the second position. Here it is. Okay, so but maybe what's happening here is that, you know, we can produce, you know, the output states in the opposite order, and then we'll just swap the order, right? So I'm able to produce this thing. Here it is. So now can I reproduce this thing in the first register so that I can swap the registers afterwards? So I'm almost there, right? I have the 0.J1 and here's 0.J1, but now I need to rotate in this J2, right? How do I add this extra phase J2? Okay. So so this is kind of good, right? This produces, you know, this first half for me. But now the question is, you know, how do I do this J2, right? This J2 here is missing, right? I need that J2. So luckily, whenever you want to rotate a phase into a single qubit state, a relative phase, it's very easy. Luckily, rotating in a phase is easy. Okay, so how do I want to present this? I want to say that okay, so if you want your phase to be theta in the reals, I mean, you can, of course, you could restrict yourself to something between 0 and 1. So let me just, without loss of generality, the phase is between 0 and 1. Otherwise, we just wrap around the unit circle. So we can use the gate R theta, which I'm going to define as the diagonal gate 0, 0, e to the I, e to the 2 pi I theta. Okay. So, you know, if you want to formally convince yourself that this is unitary, go for it. I encourage you to try and be clever and think about your tricks, right? Which said, remember, how do you know if something is unitary? Well, unitary operators are going to be characterized by, it's certainly diagonalizable first. Let's be clear, it's diagonal, right? So once it's diagonalizable, unitary operators are characterized by having all eigenvalues lying on the unit circle. And that's exactly what you're looking at, because, you know, if it's diagonal, the eigenvalues are sitting on the diagonal and they're clearly all on the unit circle. So this is unitary. Okay. And, you know, what this will do is, you know, if the action of this thing on, you know, 0 is just, well, nothing, right? It's just, remember what this does is when I apply the matrix to the first column, right? This ket 0 just rips out the first column. And when we do this, it will give me a phase of e to the 2 pi I theta 1. Okay, so it's exactly what we're looking for. Okay. And so what you can do is you can try to insert a phase, right? So there's a slight complication, which is that, you know, I have this expression here, but I'm looking for this one, right? I'm missing the J2, right? So here I need to rotate in J2, right? So I can do that using a phase gate, right? I can just inject that in here as a relative phase. The only problem is, you know, this is the first register I'm acting on, but J2 in my original state, over here, you see it sits in the second register. It doesn't sit in the first register. So in order to rotate J2 into the first register, I'm going to have to do some sort of joint operation on both registers, right? Controlled on the second one, I want to rotate a J2 into its right slot here. So let me just give you the circuit then at this point. It's going to look like this. J1, J2. So this is going to be a QFT for up to reordering of the outputs, qubits. Okay, so let's take this. And what we're going to do is the following. So remember that J2, right, this guy was easy, right? This guy correctly reproduced this thing. So, you know, when I look at the second input here, all I needed to do was inject J2 as a phase here, and that was just a Hadamard. We've already discussed this. So what I'll do on the second wire is I'll do a Hadamard here. Okay, and so that's all I need to do there. And what I know I'll get there for sure is going to be this thing up to normalization, e to the 2 pi I, 0.j2. So that's good, right? So that is precisely, this thing over here. Check. And now what I wanted to do is, I also need to put a Hadamard here, right? Why? Because that will rotate in the J1, right? If I just want to prepare this state, that was just a Hadamard. I did this, right? Right here. So when I do this Hadamard, that this adds the J1 term in the exponent. So I should say 0.J1. Okay, so I get here, but now I need to rotate in the J2, and the way I'll do it is that it's got to be a phase, and the right choice of angle to take is 1/4, right? So why do you see a quarter here? Well, intuitively, you want to put J2 into the second slot in the decimal expansion, right? And the second slot in the decimal expansion is for the power 1/4, or 2 to the minus 2. Okay, so that's why, we have to shift it over one extra slot. And this has to depend on, it's controlled on J2, right? Because what I'm rotating here into this first register, which is this wire here, right? So this wire here is going to be this guy here. What I'm going to rotate in is going to be dependent on J2. So that's why I have this control wire. Okay, and that's it. That is literally it. And here what we'll get is 0 plus e to the 2 pi I, 0.J1, right? Again, this J1 is coming from the Hadamard. And then we have J2, which is coming from the controlled rotation. Okay, and now we're almost done. Technically speaking, this is not in the notes, but what you should do is you should swap these, right? So you should take the wires and you should basically swap them over. And then that reordering will give you the right output order, right? Because remember, what we actually wanted was to get this green thing over here where J2 is on the left and J1, J2 was on the right. And what we're getting when we run the circuit is we get, J1, J2 basically on the left is the first register. This one is on the right. So we just need to swap the wires. Okay, so that's it. That is the circuit for the n equals to 4 QFT, or alternatively the 2-qubit QFT. Okay, kind of the next step up after the Hadamard. Okay, so with the n equals 4 case in hand, we can now just scale up the analogous argument to n equals 2 to the n for n qubits. Okay, so let's just do that. Okay, so generalizing to n equals 2 to the power n. Okay. Okay, so again, let's just write down the action on a standard basis state. So I'm not going to derive these now. The analysis is analogous. It's left to an exercise. So for any standard basis state, y, right? And now, of course, this thing is in C2 to the n, right? QFT 2 to the n applied to j. What is that? So it's just 1/√2 to the n. Okay, so this is again just extracting the kth column out of the DFT matrix. So you'll have a sum over all the rows, of course, and now each row gets a different phase, e to the 2 pi I. Again, and I like to do these things in color just to help you see where the two variables come into play. K over 2 to the n. Okay, so those are the two things. And you could break this up into a product representation again, like this, 1/√2 to the n. And now we have 0 plus e to the 2 pi I. And just like before, 0.jn, so the nth most significant bit first. And then we have tensor 0 plus e to the 2 pi I, 0.jn, jn minus 1, 1, tensor ... all the way down to 0 plus e to the 2 pi I, 0. Did I do this backwards? Yeah, so this is backwards over here. Apologies. So this should read jn minus 1 and jn. 0.j1 through jn. Okay, so that's the full decomposition. And now, just for brevity, I'm just going to redefine each of these states. I'm going to give them a name, basically. So we'll call the first bracket phi n, right? I'm just going to index it by whatever list of bits shows up in the phase. Phi, the next one is n minus 1, n. And when you go all the way down the chain, right, you've got phi 1 comma n. Okay, so these are our the output of QFT to the n. Okay. Okay, so let me just be very formal about this. So where I'm defining phi k dot 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 n to be equal to 0 plus e to the 2 pi I 0.jk all the way up to jn. Okay, notice how, of course, these states are not normalized right now, right? Because they both have unit magnitude, right? The normalization is hiding out here, right? So in the circuit as well, I'm not going to include normalization. So this is the general Fourier transforms decomposition, okay, into a product of n. Given an input product state, standard base state, it outputs a product state, okay? And the QFT circuit, okay, and here I'm going to omit reordering of the output qubits in the circuit, just to keep things simple. I mean, maybe here I can sketch it, but it's certainly omitted in the course notes. So what do we have? Well, we have the following, right? We take the input state j, right? And each bit gets fed into the circuit. Okay, j is written in binary. And the last two bits are the same circuit we had before, right? If you just had a 2 qubit Fourier transform, then remember what we did is we just did a Hadamard here, and then we did a conditional rotation of R1 over 4. Okay, so maybe I shouldn't say R1 over 4 just so that it's a bit more transparent what I'm doing. No, okay, starting to lag again. Let's just give it a moment. There we go. Okay, good. Okay, there we go. Good. So there's R1 over 2 to the 2, so R1 over 4, right? So that was phi n minus 1 and n, right? And then we did a Hadamard here. Here we had the controlled operation that went like this. Okay, so this was our previous circuit, right? And the previous circuit then just prepared this 2 qubit state. Of course, now we're working with, why can I not get my eraser? Oh, there it is. And now we're going to generalize this, right? So in here, it's going to be dot, 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 so the circuit, we imagine the circuit is kind of going on. And for the very last wire, what we're going to get is, let me just draw these 2 wires, right? Going all the way to the end. So this one here, dot, 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 we just continue this. This is phi, oops, n, phi 2 to the n. Okay, this is supposed to be black. And this one here, what do I have? I've got the Hadamard. And then we'll have a rotation. 1 over 2 to the 2 is the first rotation. And then we'll continue to do more rotations, basically. All the way down to R 2 to the n minus 1. Sorry, this is 1 over 2 to the n minus 1. And R finally 1 over 2 to the n. So those are all the rotations. They'll all be conditioned on the second last wire. And the output of this one then be phi 2 dot dot dot. Sorry, this should be 1 to n now. Okay. So this should be the circuit. And now the only thing, of course, is that, so this is, let's just be clear again, you know, this is just the, down here we just have the original QFT4 circuit, right? But now, of course, we're generalizing to n qubits, little n qubits. So, you know, we have to continue this pattern where we just, on each wire, we start with a Hadamard, and then we have an increasing sequence of phase gates where the precision gets finer and finer, right? And the only thing is that, of course, here the output, phi n was supposed to come first. And here you see the first wire over here doesn't have phi n, right? It's got the last guy, right? So everything's basically in the opposite order. Phi n's at the bottom. So basically what you have to do is at the end of this, you know, I'll do it explicitly here, but it's not in the notes, is you need to basically, you know, swap all the wires into place. So this would come here, you know, this would come here, and so forth, right? And dot, dot, dot. So these are all just swap gates. Okay. So that's the QFT circuit on little n qubits. I mean, you could think about how you would do this, inverting the order of all these qubits. How many would you need, right? So I'll leave that as an exercise. Suppose you're only allowed to do 2 pairwise swaps, right? So you're only allowed to do swaps of this form. So you can only take pairs of wires and swap them at a time. How many such swaps do you need? So let's leave that as exercise. Of course, the cost of that final swap is going to be added as an overhead to the overall cost of this circuit. Okay. And just as an aside, you know, this is one of the exercises that if you want to do a swap gate, you can actually do it this way. So how do you do a swap gate, right? Suppose you don't have the swap gate at your disposal. How can you simulate it? Well, you can simulate it actually by doing, believe it or not, 3 C-naughts. Okay, so there's a claim, and I want you to prove it. Okay, one of the exercises in the notes. So again, you know, to prove this, remember, if you want to prove that this is a unitary map, right? By definition, it's 3 C-naughts in a row. To fully understand the action of this thing, it suffices to pick your favorite basis and understand its action on that basis. Okay, so pick your favorite basis and analyze the circuit and convince yourself that this is really just doing a swap. Okay. So a natural question, of course, is what is the size of the QFT and circuit, right? And so here, you know, I'll get you started. I'm going to also leave this as an exercise, but it's kind of cute, right? What is this really? Well, I mean, you very clearly see the pattern, right? It's a very simple pattern. On the first line, you have 1 gate, right? So it's the number of gates equals to, sorry, I shouldn't say on the first line, on the bottom line, right? On the bottom wire, you have 1 gate. On the second last wire, you have 2 gates, right? On the third wire, you're going to have 3 gates. You know, I'm missing a whole bunch of stuff on this wire, the second last one, aren't I? Okay, yeah, so technically I should be a little bit more careful on how this diagram is drawn, okay? So here, I do need to be careful because at some point, you know, I'm cheating a little bit in this diagram, right? There's got to be a Hadamard on this wire as well, just like the other wires. But technically speaking, there's supposed to be like dot dots everywhere, right? So at some point, technically, there's going to be a Hadamard here. And then, you know, you'll have your own rotation gates and so forth here that are conditioned on the next wire down. Okay, so I'm omitting those. But basically, it's going to be an arithmetic progression, right? You've got 1 plus 2 plus 3 all the way up to n minus 1. And then I think you should have n on the last wire, no? Because you start at 1 and there are, sorry, this should be little n, not capital N, sorry. That would be a big boo-boo, right? Do not want little n. Okay. So there are little n wires, and each time we go up by 1, so this is obviously this. Okay. So, come on, buddy. Let's go. I don't know why it's... come on. Switch back to pens. Okay. Maybe after the end of this section, I'll restart with a new Microsoft journal page because this is becoming unresponsive, unfortunately. But but let's see if I can get it to at least go to the end of this discussion. Okay, good. Plus n, right? And so what is that? Well, that's just an arithmetic series, right? So I start with k equals to 1 up to n of k, right? And what is this thing? Okay, so it's either, you know, let's see, n times, I think it's n times n plus 1 over 2. And again, this is something you're going to look up on Google or Wiki. Let's just do a sanity check. If I did 1 plus 2 plus 3, right, that should be 6. And if I do 3 times 4 is 12 over 2 is 6. Okay, so that should be the right formula. Okay, so the point though is that, you know, this is order n squared gates. Okay, for the core of the circuit itself, right? So for this component. And then of course we have the swap gates, and you know, you could probably convince yourself that certainly you're not going to need more than order n squared swap gates. Okay, so the runtime overall for this QFT is going to scale like order little n squared, okay, the number of qubits. Okay, and remember that little n is logarithmic in the dimension capital N. Okay, so what we're going to see is that, you know, what is this runtime? This is really just what? It's order log of capital N all squared. Okay, so as I promised, it's polylog of the dimension. Okay, and now, you know, we need to compare this. Compare with, you know, the FFT, right? Which requires order n log n. Okay, so the QFT requires log squared n, right? This one requires n log n, so it's exponentially bigger, right? So again, though, it's entirely misleading to say that the quantum algorithm has an exponential speedup, because of course the outputs of these two algorithms are completely different, right? When you get the FFT, right, what it outputs is a full, you know, description of the vector that's been transformed. You can access all the components of this thing, right? All capital N components. For the quantum algorithm, right, what it outputs is a quantum state whose amplitudes are the components of the transformed vector, right? So you certainly are not going to be able to access all those components at will, like the way you would with the classical transform. So these are two very different beasts, okay? Okay, so let's continue now to section 3, quantum phase estimation. Okay, so you know, in principle, now that we have the QFT in hand, you know, we can kind of directly proceed to the factoring algorithm if we like. But it's really instructive to take a big picture perspective of what's going to actually end up happening in the factoring algorithm, because the more general picture is the picture is a lot more telling. Okay, so what we'll see in a future lecture is the factoring algorithm, and that we'll see is that the factoring algorithm, at least so the factoring algorithm, just like Simon's algorithm, will have a quantum component, right, which you run, and then there'll be classical post-processing, and both are crucial. Okay, so the factoring algorithm, its quantum component is going to be a special case of the following problem. Okay, and this problem is, as the title suggests, this is definition 1 in the notes, quantum phase estimation. Also known as just QPE. Okay? And so what is the input for phase estimation? This problem. So the input is going to be a quantum circuit. So you give me an implementation of, you know, your favorite unitary. So this is just a linear operator, and it's acting on C2 tensor n, so n qubits. Okay. So that's the first thing you give me. The second thing you give me is an eigenvector, and I'm going to call this psi theta on purpose. And the corresponding eigenvalue is u psi theta, right? It's a unitary operator. So as the next exercise will have you prove, a diagonalizable operator is unitary if and only if all of its eigenvalues lie on the unit circle. So in particular, they look like this. So e to the I, and let me do this in red to emphasize the theta here, right? E to the I theta psi theta. Okay. And theta will be, sorry, let me be a little bit more, it's not exactly what I wanted to write. I wanted to write something slightly different, e to the 2 pi I theta, and the reason why I wanted to do this is because I want theta to be a real number between 0 and 1, strictly speaking, so that we can write it as a fraction, or more generally as a real number with no integer component. Okay, so theta is inclusive 0 but not including 1. Okay, so this allows us to wrap all the way around the unit circle for this phase. There you go, this guy over here. Okay, what's the output? So the output, so let's be clear, the input here are, well, a classical thing. The classical thing is the description of the circuit U, right, for U. And you also get a quantum thing, right? The quantum thing is you get a physical copy of this eigenvector. Okay, so that in principle, given the description of the circuit, you can run the circuit on the eigenvector. And the output is, what do we want? We want the phase, theta. Okay. So obviously, if you're working in a classical world where U and psi are given to you just as classical objects you've written down, like a matrix and a vector, this is trivial, right? You just multiply the vector by the matrix and just yank out the phase, right? Quantumly, of course, it's more interesting because these are quantum objects now, right? You can't just do that multiplication in a straightforward way. Okay, so I want to take just a bit of a moment to discuss the subtleties of this problem. Okay, like the first time you stare at it, it looks kind of dull, right? Okay, you have a matrix and you have a vector, and so you want to estimate the eigenvalue. Like, who cares, right? It doesn't seem that exciting in some sense, right? It's not like factoring, ooh, right? But actually, the factoring algorithm is more or less a special case of this, plus post-processing, okay? And there are also many other applications to quantum algorithms. So, for example, in quantum walks, this kind of phase estimation can be used to implement quantum walks. It can be used to solve linear systems of equations, for example, via quantum algorithms. And so I want to just give you a flavor of how phase estimation shows up in some of these results, just to give you some appreciation for why this very dull-looking problem actually is quite interesting. Okay, but as we think about this, let your mind wander a little bit and think about all the the questions or the subtleties that might arise when you stare at this problem for the first time, right? So for example, the obvious question is, can we solve this problem efficiently, first of all, right? Given any U and an eigenvector, is it possible to always figure out the phase? Okay. What happens if theta doesn't have a finite representation, right? I mean, it's a real number. For all we know, it can be irrational, right? So what does it even mean then to output the phase? And the other funny thing is here is that, you have this funny eigenvector that you're given as part of the input. Like, where did this come from, right? And what if I can't prepare this efficiently? Is it a problem, right? So there are all sorts of questions that kind of show up when you start thinking about this problem in a bit more depth. So before we talk about those questions, let's just talk a little bit about applications. Okay. Oops. Okay, now obviously I won't have time to go in any serious depth here, but I just want to give you a flavor. So, the number one application, of course, is factoring, in the sense that in factoring, the application is really, I don't want to say straightforward, because obviously the algorithm is highly non-trivial, but it's straightforward, quote unquote, in the sense that basically you set up this, you cleverly set up this choice of U over here, and then you run phase estimation and just measure, and the phase is exactly kind of what you're looking for. And at that point, you just do classical post-processing, right? Whereas the later applications we'll talk about, they're a little bit more involved. There's this really slick customization of unitaries in some sense that's going on. Okay, so factoring we're not going to talk about in this lecture, but let me just give you a bit of a heads up as to how it's going to go. It's going to reduce to a problem called order finding. Okay, and what is order finding? It says, you're given as input two non-negative integers, or positive integers, I should say. The question is, what is the smallest positive integer r such that x to the r is equivalent to 1 mod n? Okay. And so roughly speaking, in factoring, if you could solve this problem, it turns out you can solve the factoring problem. Okay. And quantum algorithms can solve this order finding problem. Okay, and roughly speaking, the idea is going to be is you define a unitary u x. Okay, sorry, and this is so this is given the input x, right? That comes from the order finding problem, right? So given your x, you're trying to solve order finding. You define u so that its action on a standard basis is just this. It just multiplies x by y mod n. Okay, and n is coming from up here, right? So here's your x and here's your... So x is fixed and y is kind of the input over here. This is y over here. Okay, so the unitary is just this. You define this unitary, and then you basically run phase estimation on this unitary, extract a phase basically, and do post-processing on it. That's the very rough idea. I mean, there are many details that are missing, but this is kind of, in some sense, the most quote-unquote naive application of phase estimation, in the sense that you just run phase estimation, rip out the phase, and just do classical stuff at this point. Okay. Nevertheless, let me really emphasize here that the classical post-processing in the factoring algorithm is crucial, because it turns out that okay, well, let me leave that to the factoring algorithm lecture. Let's not get too sidetracked here. The second application I want to quickly tell you about is quantum random walks. Okay, and this will be a little bit more of a flavor of some more advanced things you could do. Okay, and so maybe you've seen classical random walks before, maybe you haven't, but in a classical random walk, it's kind of exactly what you expect, in the sense that you're given a graph G that you're going to walk on, basically, and a starting vertex. Okay, and what you do is in each time step, basically, you pick a random neighbor of your current vertex and you move there. Okay, maybe I should be clear that this is coming from the vertex set. In each time step, go to a random neighbor of your current vertex. Okay, so that's a classical random walk. Okay, and for quantum random walks, there are various different ways you can kind of implement these things, right? But there's this nice kind of not centralized, I guess, but general framework, I should say, that basically uses phase estimation as a subroutine to implement the walk. Okay, so it sets up a careful unitary and does phase estimation on the unitary. And, for a quantum random walk general framework. So this is, again, I don't have time to go into the details of how this works, but, it needs, as a subroutine, it wants to reflect. The subroutine is given a vector psi. It wants to be able to reflect about psi. Okay. So what does reflect mean? I mean, reflect just means something like this, right? In 2D, if I had my vector psi over here, right, this is psi, then reflect basically means that, if I have any other vector in the space, like maybe this one over here, then this one goes over here, right? So it gets reflected about psi. And so what is the linear algebraic way we can represent that reflection about psi? It's very, very simple. So you want to implement the operator, and we'll see this again later, certainly when we talk about Grover's algorithm. You want to implement 2 psi minus identity. Okay, and this is actually a unitary. Okay. Oh, sorry. I didn't want to call it that. I wanted to call it something slightly different. I wanted to call it r psi because we're reflecting about psi. Okay. Okay, so so what does it mean to be a reflection? Just very briefly, the idea is that if I apply r psi to psi, then nothing happens, right? And that's what you expect. Like if I'm in this picture, right? I mean, okay, maybe it's a bit more instructive if I were to draw it slightly differently, right? If I were to let this be the vector I want to reflect about, well, then if you input that vector psi into the reflection, then of course nothing should happen to it. That's what's going on here. But if you give me any other vector, like this one again, then what does it do? Well, it basically, to do the reflection, it just hits its y-axis coordinate with a minus sign, right? And so more generally, if you give me anything that's orthogonal to psi, what it should do is just inject a minus sign, right? That's kind of all the orthogonal components will get a minus sign. So this just means that psi perp is equal to 0. These two are orthogonal. Okay, so I'll let you verify that indeed, you know, this operator I wrote down here is indeed a reflection. And again, we'll see this later when we go to Grover's algorithm. Okay, and so what's the deal here? I mean, the deal is that to simulate this operation here, what I can do is, if only I had some way of breaking down, you know, the Hilbert space of all 2 to the n dimensions in terms of, you know, psi versus its orthogonal complement, then I could, you know, manually kind of insert the phase +1 or -1 as needed. Okay, roughly, very roughly speaking, right? And that's exactly what phase estimation allows us to do, because when you give me a state and a unitary, like so, if you know, if you give me psi or something orthogonal to psi, let's say, and you give me the implementation of r psi, right? Then in principle, I could run phase estimation on this thing, right? And I can figure out what is the eigenvalue, okay? And based on the eigenvalue, I could tell whether you're psi or you're in some space orthogonal to psi. Okay, and then based on that, I could inject a relative phase as needed. Very roughly speaking, this is the idea. Okay, so phase estimation gives us a way to kind of take more generally an arbitrary state psi and break it into you know, the spectral decomposition or the eigenbasis for the operator r in this case. Okay, kind of on the fly. Good. The last thing I want to mention is powers of unitaries. Linear systems. Okay, so this application is going to be more akin to the random walk one rather than Shor's algorithm. And you know, the idea here is as follows, right? So first, let's do powers of unitaries. Okay, so suppose you're given access to a circuit for u, but maybe you don't want to implement u, but what you really want is square root u. Okay. So can you simulate root u using just u? Right? Is there some way to take the circuit for u and hijack it, basically, so that you simulate square root of u? Okay, and the answer is yes, you can, right? Otherwise, we wouldn't be talking about it. And you know, the exercise that kind of gives away why this is true is just remember that if the kth eigenvalue, let's just impose some ordering on them, of u is e to the I theta k, right? Then the kth eigenvalue of square root of u is e to the I square root theta k. Okay, so you literally take square root, so you apply your function to the phase, right? Sorry, I'm being stupid, right? This is completely rubbish. You have to take the square root of the entire phase, right? So the square root of the phase, you have to take the square root of the full eigenvalue, right? So it's e to the I theta, right? But what does it mean to take the square root of this unit vector? Well, that's just going to be e to the I theta over 2, right? I mean, it's just, this is the same thing as e to the I theta all to the power half, right? So that's the, sorry, I apologize. That's the correct square root, right? Okay, so basically instead of implementing u, which has these eigenvalues, you want to implement something that is the exact same eigenbasis, but the eigenvalues are just, the phases are all divided by 2. Well, guess what? If you could do phase estimation on u, you could get access to those phases theta, right? And then you could manually kind of do surgery on them and divide them by 2, is the rough idea, right? So what you do is, again, I'm not going to write anything down. It's just going to be a friendly discussion, right? Is that you can run phase estimation on u, okay? And that will allow you to, extract all the phases theta out, basically, of u into like some classical register as a string. And then you take those phases and you apply whatever function you like to them. Like some, in particular, you might want to, divide them by 2, okay? And then you undo the phase estimation to essentially, quote unquote, hand-wavingly way, reinsert these phases back into the operator. So that now, this entire thing taken together is simulating a square root u rather than a u. Okay, so, very roughly speaking, I like to call this idea eigenvalue surgery. Because what it's doing is you're ripping out the eigenvalues, you do something kind of classical to them coherently, and then you do some sort of operation that, reinserts these eigenvalues back into the operator. What in the world did I write? Okay, surgery. All right, so, and the other one is, solving linear systems of equations. Okay, so here you want to solve this, right? So you're given, a matrix A and some target vector B, and you want to find psi such that A psi equals B, right? Very roughly speaking, this is the goal of solving linear systems, right? And of course, the way you solve this, generally speaking, assuming A is full rank, is you just apply A inverse to both sides, right? And you get this, okay? And again, what are the eigenvalues of A inverse? What are they? Well, this is just nothing other than, you take the ith eigenvalue of A, right? And then you invert it, right? I mean, if you, assuming A is diagonalizable, of course, that's how you get to the eigenvalues of the inverse. And then the eigenbasis stays exactly the same. So the principle is just the same as the square root trick here, right? So if you want to kind of simulate this inversion process, very roughly speaking, what you can do is this phase estimation trick again. You extract the eigenvalues of A into a separate register, you invert them manually, and then you reinsert them back into A, if you will. I mean, I'm waving my hands a lot here because, of course, first of all, A doesn't even have to be unitary, okay? It doesn't even have to be Hermitian, actually. And like here, it's a bit different because, well, I mean, if I take theta and I take divide by 2, these are still going to be eigenvalues on the unit circle. So what I'll get is still going to be a valid unitary operator, right? So everything will work very nicely. In the picture of linear systems, it's a bit trickier because, A doesn't even have to be unitary to begin with. So the reinsertion process requires something called post-selection. It's going to be a little bit more advanced. You cannot do it with certainty. Okay, but again, the point is very simple. Eigenvalue surgery. Okay, you want to implement some funny function of an operator like the inverse. You extract the eigenvalues, you tweak them manually, and then you put them back in. Okay? Okay, so that's just a very brief whirlwind tour of some of the applications, the many applications of quantum phase estimation. And now I want to talk about algorithms. All right. That is the straightest line I've drawn without a ruler all course. Okay, so in our discussion, I'm going to assume for simplicity that the phase theta is representable exactly using n bits. Okay, and at the end we'll talk about generalizations, but we won't go into any detail. Basically, the analysis can be extended to work even if theta is irrational. Okay, so let's just assume for our discussion, because all the ideas are kind of already there, and the algorithm will more or less be the exact same. We'll assume the phase, and so let me remind you that how this works is you're given u, you're given the eigenvector psi theta, such that u psi theta equals to e to the I theta psi theta, and your goal is that you want theta. Okay, and remember that this is something that's strictly between 0 and 1. Okay, so it's some number smaller than 1 in particular. Okay, so we'll assume that the phase theta in that range 0 to 1 can be represented exactly via n bits. Okay, so in particular what that means is that if I want to write this thing out in binary, it's between 0 and 1, right? So there's going to be a decimal involved. And it's going to look like theta 1, the most significant bit, and then you get to the least significant bit. And, you know, I'll usually try and write the subscript 2 to really stress that this is binary. So this is a number smaller than 1, of course. And, you know, if this is theta itself, right, it's a number between 0 and 1, then of course, you know, if I wanted to kind of move everything to the left of this decimal point, well, I've got n bits to shift over, so I have to multiply by the power 2 to the n. So 2 to the n theta will just simply be the bit string, this thing. Okay, so now it'll be, of course, a number bigger than 1, but, you know, that's fine. It's just some bit string, and the point is the following, that what is our goal? We want to have, given u and psi theta, we want to prepare a quantum register containing those bits, theta 1 through theta n. And so, you know, briefly, this is 2 to the n times theta, to be precise. Okay, so it's not the decimal version, it's just give me the string of bits. Okay. Okay, so that's the goal. And now let's talk about the algorithm. And, you know, the algorithm, at least in the most kind of restricted sense, is super simple. Okay, I mean, it doesn't sound like it's going to be simple, but once you have the Fourier transform, that's the main workhorse, if you will. Okay. So let me remind you, it's going to be important now. So recall that if I take the quantum Fourier transform, right, of theta. So what I want to remember is, I suppose technically speaking, I want to talk about, okay, so let me be very clear that, you know, if I take the quantum Fourier transform of the bit string theta 1 to theta n, right, this thing over here, right, before we did this using j's in the previous notes, but, you know, now I'm talking about theta, so let me write it with theta. Then remember that, you know, the straightforward formula was 1 over root 2 to the n, sum over k equals to 0 up to 2 to the n minus 1, and e to the 2 pi I k theta over 2 to the n k. Okay, so that was just plug in the formula for the kth column of the Fourier transform. Or sorry, not the kth column, but the thetath column. If I treat this bit string as an integer, right, then that's that column from the Fourier transform. And we also showed that, you know, this can be broken down into, maybe I'll need a bit more space for this, 1 over square root 2 to the n, and we had this product expansion, right? Okay, that is terrible. 0 plus e to the 2 pi I 0 point theta n 1, and then 0 plus e to the 2 pi I 0 point theta n minus 1, sorry, theta n 1, and finally dot 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 0 plus e to the 2 pi I 0 point theta 1 to theta n 1. Good. Okay, so this is just from before. This was the action on of the QFT on an arbitrary standard basis state, such as, you know, the string represented by theta 1 to theta n. Okay. So, I mean, the naive goal is going to be the following, right? If only I could prepare, I mean, there are two equations here, right? I've got star, right? And then I've got this one over here, star, star. So two different ways of expressing the right-hand side. So let's start with this one. If only I could somehow prepare this superposition involving theta, right? Then it's very easy to recover theta, right? All I have to do is, you know, this is equal to the left side, and the left side is just the QFT times this string, right? And this is what I want. So if I could prepare the right side, then I just apply the inverse Fourier transform to it, and it will, get rid of this, and I'll just recover theta 1 through theta n. Magic, right? It'll be very easy. So the question is, how to prepare the right-hand side of this equation, or alternatively, this equation too. They're both equivalent, of course. So the main question is how to prepare the right-hand side, RHS, of star or star star. Okay. And now the question now is, well, depending on how much we want to assume about u, we get kind of two slightly different algorithms. So this is the more restrictive one, in the sense that we're going to require a larger assumption on u. Okay, so I told you that as input, you're able to implement u, right? But it turns out that's not necessarily going to be enough. Okay. So let's assume first that you can implement u to the k. Well, okay, I need something a bit stronger than that. I need the controlled u to the k for any, k being some positive integer, right? Okay, so that's the first scenario. So let's assume that we're going to need a stronger assumption that you can do controlled version, just like a controlled not, same principle. But now, what gets controlled is this operator u. U to the k, let me be clear, is just the operator u k times. Okay, so to the power k. And you want to be able to do it, we assume you can do it for any possible k you want. Okay? And we'll talk about cost at the end, of course. And so once you have this, then it turns out to be essentially, almost trivial to prepare this thing on the right. Okay? So why is that true? Well, the observation, and this is the next exercise, is that, what does it mean to do u to the k times psi theta, right? If you give me the eigenvector psi theta, and you allow me to do, u to the k, what do I get? Well, it's an eigenvector psi theta, so that's not going anywhere. And if it was an eigenvector of u, it's certainly an eigenvector of u to the k, right? It'll slide through each copy of u. So what you're going to get is the original phase e to the I theta, right? Let me be precise, I've been using e to the 2 pi I theta, right? But now you're going to get it k times, right? Because you applied u k times. Okay, so think spectral decomposition. Another way to think about it is, remember, this is an operator function. We apply it to the eigenvalues of u. So here they are. Okay, and lo and behold, look at this thing over here, right? This looks almost exactly like this. So it's e to the 2 pi I k theta. Wow, magic, right? So let's just use this observation to prepare this right-hand side using the assumption that we can implement controlled u to the k for any positive k. Okay? Therefore, what do we do? So to prepare the right-hand side of star, we start with, two registers, right? Theta to the n and psi theta. So remember, this is the eigenvector. This is, we're going to eventually write theta here, which again, we're assuming in this case is going to be an n-bit string. Okay. And then what do I do? Well, let's stare at this thing, right? What is this thing over here? What is star? It's a superposition over all possible k with an equal weighting. Okay, so already this is screaming Hadamard transform, because that's how you get that. And then for each possible k, you're going to inject a phase that's directly proportional to the value of k. That's exactly what this does, right? Whatever the value of k is, it injects a phase proportional to that. So let's start by doing the Hadamard part, right? Let's first get the equal superposition over all k. So the gate we apply here is h tensor n on the first register. And so we're going to get 1 over square root 2 to the n, sum over k equals to 0, up to 2 to the n minus 1. And now I just have an equal superposition of k. So that's the part that's changed. And the part that does not change is, the eigenvector is just still hanging around. I haven't really used it yet. And now what I'm going to do is I'm going to do my controlled u to the k operation. Okay, meaning, so maybe I should be just a bit more precise. Okay, so first let's write it down here, but then maybe I'll define it a bit more precisely as we go along. So the controlled u to the k operation, so controlled u to the k, what it's going to do is it's going to read off the this register k, and then it's going to apply u k times to the second register. Okay, so let's be clear that if I have something like this, controlled u to the k, what it will do, the action of this operator is going to be k u to the k psi. Okay, so this is what we're assuming we can do in this assumption. Okay, so what do we get? We get 1 over square root 2 to the n, sum over k equals to 0 up to 2 to the n minus 1, k, and now I get u to the k psi theta, right? Okay, so but now I've got this thing here, right? I've got this thing over here, right? And that looks exactly like, trying not to draw too many arrows here, but that looks just like this, right? Huh. Coincidence? I think not. Okay, 2 to the n minus 1. Sorry, this is down here. Okay, and so what do I get? I end up getting a phase gets kicked in, right? So it's e to the 2 pi I theta. Maybe I'll be consistent with the notes here. K theta. Okay. And then, of course, I still have my k here, and I have my psi theta, which goes nowhere because it's an eigenvector. Okay. So, that's just applying this observation. And so now we just want to rewrite this state for a second. So I'm still going to have 1 over root 2 to the n. I'm still going to have the sum over k equals 0 up to 2 to the n minus 1. E to the 2 pi I k, right? And I'll put a k here. And, we can ignore the eigenvector at this point, but, maybe to kind of emphasize that, I'm going to just emphasize that these things are in tensor product now, what's in the blue brackets and what's not. And now the question is what goes over here. Well, I had theta, and I'm going to do something that looks trivial for a second, which is I'm going to multiply and divide by 2 to the n, right? Nothing changes. Right? So I can think of this as kind of put a bracket around it. And remember what we wanted to extract was, 2 to the power n times theta, because theta was between 0 and 1. When we multiplied by 2 to the n, it kind of shifted everything over and gave us the bits of theta. So that's really what I want, right? But now we're basically done, right? Because, ta-da, look at this thing and look at this thing, right? These things are essentially identical, right? I have 2 pi I k, here's 2 pi I k. I've got a denominator of 2 to the n, and what I basically need to do is I need to redefine this theta basically by 2 to the n theta, okay? And then I get exactly what I want, okay? So now what that means is that if I apply the inverse q of t, I will recover what's in the phase. Basically, I'll recover this 2 to the n theta, right? Whatever this was up here, this theta, that's going to come out. So I'm going to get 2 to the n times theta, all times k. Oh, so sorry, no, not k. The eigenvector is the one that hangs around, right? We're not using it at this point anymore. Okay, and let me just be clear here that right, we can sketch a circuit. This isn't in the notes, but the idea is what? You've got 0 to the n, you've got psi theta, right? And so these are multi-qubit registers, so you might want to write them like this sometimes. And then what we do is, we do Hadamard tensor n on this, okay? And then what we do is conditioned on this, we're doing this controlled u operation, u to the k, right, operation. So whatever, I don't want to write controlled u, so think of that as controlled u to the k. And then you're basically done, right? Then you just invert the q of t. And what you'll get is 2 to the n theta over here, and here you'll just, nothing will happen to psi, right? The whole time psi was just kind of, oh, sorry, this does not belong here, right? So boo-boo over here. the Q of t does not act on the second register. So, psi, the only thing it does is it goes through the operator for which it's an eigenvector, so it stays unchanged. Okay. Okay, so that's it for the application. Sorry, for the algorithm. And this was based on the assumption. Then I can do this controlled u to the k operation, right? So you tell me how many times you want me to apply u, and in a controlled fashion, I could do exactly that for you. I can apply u to the k, okay? And of course, let me be clear that it's trivial to apply u to the k if you know how to do u, right? You just do u k times in a row. The more interesting part is, not a lot of times, but sometimes you really need k to be very large, right? So in this particular example, you'll notice that, k is going from 0 up to 2 to the n, right? So you're going to need to be able to do u like an exponential number of times. And in general, this is not going to be possible. Okay, so we're going to come back to this shortly because we're nearing the end of the lecture now. Let me just mention that, can we relax this assumption, right? That we can implement controlled u to the k for any positive integer k. So we can slightly relax it. Okay. And how you do this, I'm going to leave as an exercise. But if you want to be less restrictive, meaning, let's assume something slightly weaker, that we can implement this controlled u to the k. Sorry. How do I want to do this to be consistent? I'm not going to do it for any power k, but only powers which are powers of 2. Okay, so I can only do controlled u for powers of 2. Okay, so it's a more restricted assumption. Okay, so it's a lighter assumption, if you will, for k greater than or equal to 0, an integer. Okay. Okay, so and it turns out that we can still do quantum phase estimation. And I'm not going to sketch it now in the interest of time. The idea is quite similar to this, except the one main difference is that I purposefully wrote down 2 equations and marked them both here, right? The quantum Fourier transform of the phase we wanted, that thing is going to be there are 2 expressions for it, and we use the first one, right? But coincidentally, I haven't used the second one, and indeed, if you start with the second one, then if you want to do the second setting here, where you can only raise u to powers of 2, right? So you have this weaker assumption, then basically you can use that to prepare the right-hand side of this thing, okay? So that's going to be the idea of the proof of how you do that. So the setup is roughly similar to this otherwise. And, roughly speaking, for each kind of power of 2 you choose, right, from, 0 up to the log of n, basically, for each power of 2 you choose, you're going to be able to prepare precisely one of these brackets showing up in the expression. Okay, so you individually build each of them, and then their tensor product will give you the full thing. So, so the idea is prepare star star instead of. And of course, there's something stupid about what I'm saying, because obviously star star and star are the same thing. But the point is that there are 2 different ways of writing the same expression, and so you're aiming to reproduce the setup as in star star as opposed to star. Okay, that's what I mean by this. Okay, so but that's all I want to say about that. We do have to say a little bit about runtime and what happens if theta is not rational, okay, or cannot be represented in n bits, okay? So runtime and discussion, okay, and I'll keep things relatively high level here in the interest of time. Okay, so but the 2 major issues are, well, one, what if theta cannot be written with n bits? Okay, so what if, theta is, pi over 10 or something like this. So it's just not even rational, right? And, we didn't do it here, but it turns out that essentially the same algorithm, more or less, will work to give you, obviously you can't get theta itself, but what it will give you with high probability is the first n significant bits of theta. Okay, so it basically gives you a very, very good approximation of theta. So let me write down what, basically how the algorithm would slightly change and what kind of guarantee one can show, and we won't explicitly show it here. Okay, so what's the point here? So the goal is going to be to compute the first n, or when I say first, I really mean the n most significant bits, right? So the largest ones, the first n bits of theta, right? So it's got an infinite expansion, so this is kind of the best we can hope for. Okay, and we're going to do it with probability at least 1 minus epsilon for, you know, pick your favorite epsilon, right? So fix some constant. Okay, so the point is that you can show, and we won't do it here, so it suffices to run the same algorithm above, except where, you know, originally we had this thing, right? We'd had zeros to the n, and then we had the state vector psi theta, and we plugged these guys into the algorithm, and so there's some big black box here, and out came, you know, the 2 to the n times theta here originally, right? That was the setup. And now, you know, since theta cannot be represented directly with n bits, you know, we have to kind of expand this register slightly. So this is register 1, except we expand register 1. So by that, I'm explicitly referring to this first kind of block of qubits to slightly more. So more than before we had n qubits, now we want to use slightly something bigger. Obviously, the slightly something bigger should depend on the error probability. Okay, so the precise expression you get is the log of 2 plus 1 over 2 epsilon qubits. Okay, so if you run the same algorithm, except, you know, here instead of having, you know, n, I'm going to have n plus, you know, the ceiling of log of 2 plus 1 over epsilon. Then, you know, you can run the same algorithm, and you can do an analysis then to show that, you know, with high probability, probably at least 1 minus epsilon, when you measure this register, you'll get the first n bits you record will be the right most significant n bits of theta. Okay. Good. So that's good news. And so how about number 2, runtime? / size of circuit, right? Because that's how we're thinking about runtime now. Okay, so, I mean, if you look at the circuit for this thing, we did draw it, here it is, right? So the dominant components here are obviously going to be, you know, this is just little n, right? The q of t is a big boy here, right? And, you know, there's this funny controlled u to the k, which we don't really know much about, right? And that's kind of unavoidable because u to the k is very context specific, right? So, you know, you can't really tell me a priori what, there's going to be no closed formula for what this costs, right, in general. Like, it really depends on which U you're thinking about. Okay, but the main components are, you know, the q of t, basically. And we know that this is order log squared n, right, which is in the same thing of order n squared, right? The Hadamards are order n. We just do n of them, so let's just omit those. They're a lower order term. And then we have this controlled u to the k operation. Okay, so now we have a bit of a problem. And the problem is that, you know, if you look at the circuit over here, right, if I wanted to get n bits of precision, right? Here's my circuit for n bits of precision. I prepared n qubits in this first register in 0. And if you look at the step where I do the controlled u right here, right? I raise u to the power k, and what does k do? Well, k goes all the way up to 2 to the n minus 1, right? It's exponentially big. So in general, I'm not going to be able to raise arbitrary u to an exponential power efficiently, right? By efficient, I mean with the number of gates as polynomial in n. Right? Intuitively, this shouldn't be possible, right? I mean, otherwise you're somehow fast-forwarding time, right? So we hit a little bit of a snag here, right? That's a very important consideration to consider to always remember when you use phase estimation. Okay, so so here's your snag, right? So to get n bits of precision for, you know, our estimate of theta, right, need to run something on the order of, you know, c2 to the n, right? It's going to scale exponentially basically in n. Okay, and you know, there's a nice little exercise I leave here. I'm not going to do it here in the lecture, but you know, it's probably a great thing to do in the tutorial, or maybe even I can put it on the homework. But you know, it's just to kind of convince you that in general, you know, you cannot expect to be able to, you know, given an arbitrary u, to be able to raise it to exponential powers in some efficient manner. Okay, so suppose the exercise basically says that suppose given any unitary u and k, let's just say k is in the range you know, 0 up to ... 2 to the n. Okay, we can implement u to the k in poly n gates. Okay, so the claim is that if you can do this, then you can do some things which complexity theoretically should be impossible. And in particular, you can show that, prove that this allows you to count the number of solutions to a SAT formula, or I should say to any SAT formula phi. Okay, so think of your favorite SAT formula phi. It's NP hard to figure out if he even has one satisfying assignment, right? But to count the number of satisfying assignments is even harder, right? That's sharp p hard. Okay, and so I claim that if you have this ability, right, to raise u to exponentially large powers efficiently, meaning time polynomial and little n, then you could count very quickly in polynomial time in little n the number of solutions to any SAT formula. Okay, so that's extremely unlikely. So this is, you know, a way of trying to convince yourself that indeed it's going to be very unlikely to be able to do these very high powers of u for arbitrary u efficiently. Okay. Okay, so that's the snag. So the good news is that we can compute order log n bits of precision. Yeah. Precision of theta. Okay, so in particular, that means I won't get all of theta, of course, but I'll get the first log n bits, basically. And, you know, there's an exercise here, and the exercise basically says that, you know, call this estimate, if we call the first log n bits, right, so maybe I'll be slightly more precise here, theta tilde equals to, you know, theta 1 ... So, okay, we should be slightly more precise here in the sense that I should say 0 point theta is equal to 0 point theta 1 up to theta log n, right? So if you just truncate after the first log n bits, then, you know, how big can this error be, right? Okay, and you know, basically, if you think about it a little bit, you'll see that this is basically something in general that's going to scale like an inverse polynomial in little n. Okay, so it's actually not that bad at all. It's quite good. And so this is, of course, something you could do efficiently because if you want log n bits of precision, remember, you know, if I want whatever the number of bits of precision I want, I need to run u to exponential and that, right? So if I want log n bits of precision, then I need to run u to 2 to the log n, which is just n. Okay, so this I can do efficiently. And, you know, the good news is it won't be that far off in terms of the estimate of theta tilde. And, you know, as a very rough rule of thumb, like typically in quantum computation, for many things, like when we define complexity classes like BQP, which is like the quantum analog of P, now these circuits cannot distinguish states that are closer than 1 over poly anyway, in terms of, say, the Euclidean or trace distances, okay? So, you know, often 1 over poly distance is actually good enough. Okay. Now, well, okay, maybe I'll leave this, I have 2 comments left, maybe I'll leave that comment to the very end. So let me just, the first comment I want to close on in summary. Okay, so if you, number 1, if you want n bits of precision in phase estimation, you need to be able to do u to the n. Okay, so for arbitrary u. Okay, and for specific u, of course, you might be able to get by with less if u has a lot of structure, right? But in general, you know, you have to always keep this in mind when you're using phase estimation. Okay. The second thing is that for factoring, we actually do want n bits of precision. Okay. Okay, so, you know, sad face. Ha. Okay, so there you actually need this n bits of precision, but there the catch is going to be, luckily, the specific choice of u we apply, right? I mean, here it is, by the way. I remember we wrote what u was, right? What was u when we discussed the applications of this phase estimation? Very briefly. Okay, well, let me just, no, I didn't pass it. Anyway, let me just write it again, because it's just going to take a second. Okay, but here, the unitary u we defined was this, right? Basically what it did is it took us, you know, an integer y and multiplied it by x, mod n. So this is just a very special classical operation that, of course, we're going to do coherently in superposition. And this thing here, it turns out like this kind of multiplication and then taking a mod, this can be done efficiently to extremely high powers, okay? And there's a classical algorithm for this known as square and multiply, which is extremely efficient. So you could raise this unitary u to the power 2 to the n just by essentially encoding this classical algorithm into quantum gates, basically. Okay, so there you do need n bits of precision, but it turns out that u has enough structure that you can get around this problem. Okay. Good, so that's the end of this lecture. As a quick recap, we talked about, again, maybe after the entropy lecture, this is the other second most important lecture, by which I mean that, you know, even if you never look at quantum computing again, you know, things like entropy, things like the Fourier transform, they're, you know, ubiquitous in many fields of science, and the Fourier transform in particular has a huge impact on your everyday life. And so, you know, the goal of this lecture was really to kind of impress upon you that impact, to talk about where the Fourier transform comes from, like from these Vandermonde matrices. Some of the things it's useful for, like multiplying polynomials quickly. And then how we do a quantum Fourier transform, how do we implement the classical Fourier transform basically on a quantum computer. And finally, how do we use the Fourier transform to do quantum phase estimation, which in turn has a number of applications which we try to briefly outline. Okay, so that's it for this week. Hope you guys have a good one. Stay healthy and let us know as usual if there are any questions.